Somehow on my YouTube channel, I have 52 subscribers. I don't know where they came from. Random, I just keep getting random subs. Maybe we'll get a lot of people watching. Who knows? But okay, today we're going to do renormalization or begin renormalization. And we've sort of been doing quantum field theory in the dark, so to speak. So for example, we've worked with objects like coupling constants. We've worked with objects like masses and coupling constants, and those turn out to be not the right mass or the right coupling constant at all. In fact, we've sort of been working with fake masses and coupling constants up until this point. And it's not really until you go through this process of renormalization that you get the right parameters in your theory. So from a basic standpoint, we know what renormalization is. It's to get rid of infinities, right, in these integrals. And Johnson has gone through dimensional regularization, I think, with you guys. So that is a good technique. That is one technique to renormalize a theory. But today I'm going to talk more generally about renormalization. What is the general process? And then next week, we're going to cover the renormalization group, which is a very, very important idea. And I'm not going to spend too much time. So we're going to do renormalization this week and next week. And then we'll just jump right into QCD, Yang-Mills theory, and symmetry breaking. Actually, we'll do symmetry breaking next week. Yeah, symmetry breaking is a good topic. So, okay, so here's the homework. Okay, it's 32, 33, 34, and then 31 from Lancaster-Blondel. And also add the additional chapter. I forget the number on symmetry breaking. I don't remember the chapter number in there. Okay. I think I've assigned 32 before, but you know, it's good to give it another read. I will closely be following. Actually, I'm almost exactly following Lancaster-Blondel for renormalization. I really like their treatment of the subject. The other books are very complicated. I think you should just get a sense of what's going on because it's so important that I don't want to make it. So you let me know if today's lecture is easier than the ones I've written from scratch, okay? So at the end, you let me know. Let's see. Okay, any questions about anything we've done already before we get started? Also, one more logistical note. Johnson's going to do vacuum polarization today. And then he's not going to do a few sessions. He's going to take a few weeks off because I'm going to have you guys get started on a research problem tomorrow. And that's what you'll work on the next few weeks on the side together as a group. And then when he comes back, then he'll teach you abstract algebra. I don't know if he mentioned that, but yeah. So he'll teach you some more mathematical stuff instead of physics, which is what he's good at anyway. I've sort of made him learn quantum field theory because he's only taken like very basic quantum mechanics. So for him, he's really learned a lot of the physics with you guys. So we always have conversations about it before, which is good. Okay, very good. So what are divergences? What are divergent integrals? I think it's important first to get the mathematical form, okay, of what a divergent integral is. Okay, so what are some divergent integrals? So the first one would look like this.
Your video isn't pinned.
Oh, it's not? Wow. I thought I was good and I pinned it before. It says that I have to spotlight. There we go. Oh, geez. See, there's a difference between pinning and spotlighting. That's something I've realized too. Okay, so if I integrate this guy, what do I get? It's really straightforward, right? I just get x to the n plus 1, and then this is the power rule for integration over n plus 1 from a to infinity, right? So this is not a good integral because this diverges for n greater than or equal to 0, right? You can just very clearly see that this is going to have a problem because this term is going to grow exponentially. This term is going to grow much slower. Therefore, this thing blows up, right? This fraction blows up. Okay, so this is a very simple example that any calculus student, very basic calculus student, could understand, right? So this is a divergence. Okay. And then we have the more famous divergences, which we are used to in a QFT context. And those are our logarithmic divergences. So we have some dx over x, and we know that this guy yields ln x from a to infinity, right? And these are our so-called logarithmic divergences, right? These are very popular in QFT. And then we can also have, well, what's an example of a convergent integral? Maybe we should look at one that actually converges, because at tree level, nothing diverges, right? We have convergent integrals. We can do the integral. So here's an example of a convergent integral. So basically just flipping this top one the other way around. So you just get dx over x to the n. Okay, and you can do this quickly. And this is a convergent integral. What do we get? You get x to the minus m plus 1 up top, right? Because this is going to be, this is a fraction. It's going to be over that thing, right? And then you get minus m plus 1. Wait, yeah. Okay, and this integral converges. There's no divergence at all, no problem. So these are some examples of divergent, well, these are divergences. This one's very popular, and we find that at loop level, we always get divergences. What's a very simple divergence? What would be one very simple way to tell if your integral is going to be divergent? If you have more powers of momenta up top than in the bottom, right? If you have more powers in the numerator than in the denominator, your fraction is going to grow very fast, right? So that's a very simple way to say, okay, I have a divergence. Okay, are we clear somewhat on the mathematical thing that we're trying to, I mean, it's fairly obvious, but you see, this is something I usually wouldn't do, but Lancaster Blundell very nicely show you these things at the beginning of their chapter. So, okay, that's kind of neat. So I said, okay, I'll show you them too. Usually I would just assume you knew these guys are divergent and say, okay, this is a divergent integral, but okay, we can go a little slower. It's okay. I'm not on any. That's the benefit of this format. We don't have the pressure of taking exams or anything. I mean, I don't. Unless you guys want exams, it's up to you. Okay, so let's talk about renormalization from the very first principles. Now that we know what divergent integrals are, let's start with phi to the fourth theory and renormalize it and get the right mass and get the right coupling constant. Okay, so what is the Lagrangian for phi to the fourth theory? Well, that's just 1/2 d mu. That's just 1/2 d mu phi squared minus 1/2 m squared phi squared minus lambda over 4 factorial phi to the fourth, right? That's our standard Lagrangian for phi to the fourth theory, right? Hopefully that's okay with everyone. And let's write down in phi to the fourth theory, let's write down the first 4 Feynman diagrams, okay? So Feynman diagrams, tree level and loop level, okay? And let's write down the S channel, T channel, and U channel diagrams, okay? So let's do that. So what is the tree level diagram? Is very simple. Something that looks like that, right? That's tree level. And very simply, I have some P1, P2, P4, P3, right? And that is a very, actually, let's do this way, because these guys are going in. So let's call these P1 and P2. Let's call this P3 and P4. Okay? And can someone tell me the amplitude of this guy? Oh, where the vertex factor is minus I lambda, right? Just our standard 5 to the 4th theory. I'll ask you the amplitudes after, actually. Okay, so now let's draw the S-channel process. So what is the S-channel process? You guys can draw it, and then I'll draw it and see if we get the right thing. Okay, so the S-channel process is very simple as well. You just get a little loop here and an additional vertex. So this is still P1, P2, P3, P4, except this we'll call Q, right? Because that's the internal momenta. And then we'll call the momenta going in here, P1 plus P2 minus Q, right? Into this vertex. Similarly, the same thing here, except Q minus P3 minus P4. So this is the S-channel process. Okay. Let's write down the T-channel process. That just flips this guy just flips it this way, right? That's what we're doing in the T-channel. Right. And again, now we get P1, P3, right? Because now they're going in from this way. So this is P2, this is P4. The internal line is still a Q, right? And we get, I'll do it like this. We get a Q, and we get P1 minus P3 minus Q in the internal line. And this is the T channel. Cool. Very standard, nothing. Okay, and then the U channel is a little bit more complicated, but not really. You just have a little bit of crossing. So let's draw the U channel, and you guys can scribble it down before I write it. Okay, so the U channel is sort of the same kinds of ideas, except now we get the loop down here, and then we get some sort of weird crossing, right? Between the particles. That's the only difference. So P1, P2, P3, P4, two vertices, right? So that's where the internal line is going to be. And very simply, we have P1 minus P4 minus Q, and we have Q. Okay. We good? I hope this isn't too complicated. Yes? Okay, very good. So now the idea is let's write down the full 4-part amplitude, okay, in 5 to the 4th theory. So we'll follow the Feynman rules of 5 to the 4th. Let's see where we get divergences and let's correct them, okay? And then you can apply the same rules to QED, to QCD, to any theory. It's just a little more complicated in finding the right terms to cancel the divergences. However, you know what, I keep saying that, right? And in physics, we often do this. We say that you need to cancel the divergences, right? As if we don't, there's no consequence of that. There is a physical consequence to canceling the divergences. You cannot, it's not like gauge symmetry, right? Where gauge symmetry, there's usually no physical consequence, right? Is that something that makes sense to you guys when I say that? Right? What is gauge symmetry? If I take a collection of vectors in a field, right, and I rotate all of them, is there any physical consequence to that? The physics will stay the same, right? But if I'm going to shift my parameters fundamentally here, that is going to have physical consequences, right? There's a difference. Renormalization, in other words, it's not just getting rid of infinities. Okay, there are other, which we're going to see. So just keep that in mind. I'm going to explicitly tell you. It's not just like I'm just canceling the infinities and get, I mean, that seems very crazy. I mean, you must, so if you're going to fundamentally change the mathematics, then you're going to get something back out of it, which we're going to see that structure. Just keep, it's not like gauge symmetry. That's all I'm trying to say, where we exploit that. Okay, very good. Okay, let's write down these amplitudes. How about that? Let's do it. Okay, can someone give me the amplitude of the first diagram? That's the only one I'll ask you guys because it's so simple. So what is, we'll call that 1. What is IM1? There's only one object. You have to tell me.
Minus I lambda.
Yes, thank you. That's it, right? Because there's 4 external lines and just 1 vertex, right? Okay. Now we can just follow the rules. So I'm not trying to trick you guys. Now it's just very, that's the beauty of the rules. Now we just follow the 5 to the 4th rules. Okay, let me write down the amplitude of the second object, okay? So, so this is the first one. Now let's do the second one. It's going to be some integral from 0 to lambda. Don't worry what this lambda is yet. I'm going to tell you what this lambda is. You guys probably already know from your basic experience with renormalization, but the basic idea, we're going to have some d4q over 2 pi to the 4th, right? That's just our standard normalization. I over q squared minus m squared plus I epsilon, and then another propagator I. Can someone tell me the momentum, the denominator? Well, it's just going to be some p minus q squared, right? Okay. Minus m squared plus I epsilon. Okay, that's the basic idea. And when you integrate this, you get minus 4IA, where A is just some constant. Well, don't worry about that yet. ln, you're going to get a log. That's how these integrals go. Lambda over p. That's what you get when you integrate that. And of course, this integral is proportional to d4q, q to the 4th, and it is logarithmically divergent. Okay, so let's just say for now that lambda is some large momenta that we let go to infinity. Okay, we want it to be some large momenta. It's not exactly a cutoff. We're not exactly cutting off the momenta yet. We're just saying it's some parameter we get to go to infinity, but you can clearly see that this guy has a problem. It is logarithmically divergent. Okay, because this log takes the form of the first integral that we saw. Is this okay? This amplitude's okay to construct? Nothing crazy. We get 2 propagators because we have 2 internal lines, right? One going there, that have different momenta carrying different momenta that they carry. So okay, this is the general form. I haven't picked out a Feynman diagram yet. Okay, I'm just giving you the general form of these divergences, right? Now the S channel, the T channel, and the U channel are all going to be logarithmically divergent, right? The only difference now between, because they all have the same sort of loop structure, the only difference now is that the labels are different in the ST and U channel, and that will be reflected in the amplitude. Okay, so I'm going to write down the amplitude for, I forget what, I'll write the amplitude for let me see which one I'm going to do. For the S channel, and you guys see what I write and then try and copy it for the T and U channel, okay? Okay, so I'll call that M2, the S channel, and let's write down the amplitude, okay? Okay, so this is the basic principle now. Obviously, I'm gonna do the integral. I'm not gonna write out the integral. This is post-integral. So I'm gonna obviously get some IA lambda squared. This just comes from the two vertices, right? In phi to the fourth theory. With some random constant A, then I'm gonna get ln lambda squared. I'm just following phi to the fourth theory. I'm just trying to remember what the answer was. Yeah, minus ln P1 plus P2 squared. I'm fishy on this term. I'm trying to remember why. Let me erase these. These are going to get annoying. Okay, because if you recall in the S channel diagram, there was a term that had P1 plus P2. Right, and I can just write this in a nice, this is basically the amplitude once you integrate it. It's a very simple expression. And when I write that out, I get IA lambda squared, ln lambda squared, minus ln s, okay, from the S channel. Okay, that's the basic process. No secret that this is logarithmically divergent. Okay. Okay, and similarly, we'll call IM3 the T channel. It's the same, I won't make you do it. It's the same expression except you get a T. Okay, and it's the same expression except you get a U. Okay. So do I have to write it down or do we? Okay. It's just the same. They're the same integrals, right? This is why I get why we have different channels because they're describing different processes. But in a sense, doing this on paper is sort of, it's more important in QED, right? Because you have antiparticles and crossing symmetry and all of that. That's why I don't show you Mandelstam variables in scalar field theory, because it's very kind of trivial. I hope you're seeing that. In QED, it is not trivial because antiparticles, sign, blah, 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 blah. No, in scalar QED, this procedure is very trivial. You literally get the same expression. In regular QED, you will not get the same expression. That's why we wait until fermions to introduce these kinds of ideas. Does that make sense? Okay, but it's fine. This is a nice, easy example. Okay, I'm just going to write them out just in case anyone feels a little. And all of these are, I'll show you what I mean by logarithmically divergent. But let me just write it out. So IM1 is minus I lambda. IM2 was IA lambda squared, ln capital lambda squared minus ln s. IM3 was IA lambda squared, ln lambda squared minus ln t. And what am I doing? Oh, I called it 4. Okay. Whatever. IL lambda squared, ln lambda squared minus ln q. Okay, just to be very explicit. This is exactly in the form they did in the book. I would not have done it this way personally, but okay, fine. I'll be nice. These are obviously divergent as capital lambda goes to infinity, right? These guys, this is a problem because this is a squared term, okay? Okay, good. People think that the most important thing you learn in basic calculus is derivatives and integrals. I disagree. Anybody can learn a derivative or an integral. I think the most important thing you learn in calculus is to get an intuitive feeling of what's blowing up and where functions are going at infinity. That to me is the most, as a physics person, that's a very short-sighted thing to say, but that to me is the most sort of getting that feeling. What are functions doing in certain limits? That's extremely important. Okay, let's combine this into one expression, right? We want one expression for the amplitude. So IM just equals, well, M1 plus M2 plus M3 plus M4. Does everyone get why I've added the diagrams, right? We're just literally adding the amplitude. That's in perturbation theory. That's what we do. And when you add them, you get a very simple expression. You get minus I lambda from the first guy plus IA lambda cubed, because you had 3 of those. Or wait a second, do I get a cubed or a squared? No, I get a squared because now I'm going to multiply it by these 3 terms that I'm going to add. Right. So 3 ln lambda squared minus ln s minus ln t minus ln q. Right? Because now I just can multiply this guy by all of these terms. Right? And that's the full amplitude. Are we okay with this? I hope this is not. Okay, good. So now the question, what we need to do, we have a new problem now, right? I've sort of taken the problem and made it new. Now these amplitudes depend on some new parameter, lambda. And the issue is things also blow up here as this guy goes to infinity. So I haven't resolved the problem. I just said I have some new momentum, large cutoff, but I haven't really specified where I want to cut it off. And I still want it to be large momenta. I want my theory to be able to handle a wide variety of phenomena. But the point is we need finite lambda. So we need finite lambda. That's important. Okay, where this guy is not equal to infinity. So we need to specify some place where we cut it off. Or, so that's the first option, right? I can say, okay, this guy only goes up to some numerical value, right? And that just solves the problem. Or we just get rid of the lambda dependence, right? And if we can get rid of the dependence on this arbitrary momenta, well, then we're okay, right? Then we can compute in terms of the values we have in there for momenta and so on. So what to you seems like the better way? Or what would be the more appealing way? What do you guys think? Should I try and just get rid of the dependencies on lambda? Or should I just make lambda some random number? What would be the more desirable thing mathematically? I mean, it's okay. It's okay to guess. I mean, it's fine. I mean, what would you do if I give you this problem? If you were in Los Alamos or something, no, you would be in it. You would be at some. If you were at Caltech and it was 1950, 40, no, 50s, and someone said to you, okay, you need to solve this problem. What would you do? What would be desirable?
I think we need to leave lambda, otherwise I'm really mistaken.
What did you say? Sorry.
I think we have to leave lambda, otherwise it will make little sense.
Okay, that's one intuitive way, right? Maybe, I mean, what do you mean by getting rid of lambda? Right? That's a natural question. In some sense, lambda is a totally arbitrary parameter, right? The momenta that tell me about this process are the momenta in these terms, in some sense.
Okay, then we can get rid of it, or we can try both and look what works.
Maybe so. Okay, good. So yes. So it's hard to see, obviously, intuitively, but the idea people had was to get rid of it to at least second order in perturbation theory, which is what we're working in, right? We're working in order lambda squared. You should always take a look at the coupling to see what order you're working in. That's a good habit. We're working in order lambda, second order in the coupling, right? So we're in second order in perturbation theory. Usually we always have lambda, right? We never have a lambda squared term. This is new because now we are in, actually, look, take a look how awesome this is, right? We have the first order term right there, right? And then we literally adding the second order term. So literally we're writing out the perturbation theory, right? From all of that S matrix stuff. So it's cool to see it all coming together now. And then you can, this is such a nice little marker. Lambda, lambda, and then you'd have lambda cubed, then you have lambda to the fourth, then you have, right? And you can do this in any theory. That's pretty cool. That's the beauty of field theory. It's a very simple algorithm. Okay, but putting that aside, so let's try to get rid of lambda to at least second order, first loop level. And let's see if we can do that and manage the physical, because you're absolutely right, Olha. There will be physical consequences. You can't do any, it's nature does not allow you to get away with anything. So let's see what happens. So the first strategy would be to modify the Lagrangian, right? And to add a term to the Lagrangian that's going to somehow manage this extra parameter. And that was the strategy taken, and that's the strategy that works. So let's do it. We need to modify the Lagrangian. That's the key insight. But you're absolutely right. On the surface, it seems as though getting rid of this parameter is strange. Why have it in the first place then? But there will be physical ramification, no doubt. So we're going to add terms to the Lagrangian to get rid of these second order divergences. So what happens to my Lagrangian? Now my Lagrangian is going to have one term to absorb this. And it turns out that if you add this term, which it's not very hard to see, so now we subtract this new term. It's not very, if you just work out some of the math, it's not very hard to see that a term of this form is going to get rid of the divergences or get rid of all of this dependence, so sneakily get rid of anything with this capital lambda or this new parameter. Okay. Okay, let's see where this takes us. Is this a good strategy or not? So this is a good strategy, but we're going to see why. And this is called a counter term. Okay, and Weinberg has a whole chapter on counter terms, which go into a lot of detail. And a counter term it's in the definition. A counter term counters the divergences. So the idea is you add counter terms to the Lagrangian in order to curtail the divergences. Okay, so let's write the new Lagrangian, this time with the counter term. Okay, so again, our Lagrangian is 1/2 dv phi squared minus m/2 phi squared minus lambda over 4 factorial phi to the fourth. And now we get an additional term. That's now I put a plus because this guy has a minus sign anyway. Okay, so take that with a grain of salt. And we'll call this C. We'll put a 2 because it's the second order in perturbation theory over 4 factorial phi to the fourth. Okay, this is the new Lagrangian. Okay. It seems almost too simple of a fix. So obviously I have to talk about this more. This seems totally crazy. Okay, of course. Well, let me explicitly write down C2. So C2 is equal to minus 6a lambda squared ln lambda. Okay. Just to explicitly tell you what the counter term is here. Has nothing to do. The 4 factorial is just Wick theorem stuff, which, you know, it's very strange how combinatorics came into quantum field theory, but it did. A lot of mathematics that was extremely strange came into quantum field theory. Okay, now it might be useful to see what happens to the S matrix, right? Or Dyson's expansion in this situation. So let's do that. Let's see what happens to the S matrix. So what happens to S hat? It's pretty straightforward. We get some time ordered product of e to the minus I, right? So this is just Dyson's expansion, or Dyson. This is what I'm just showing you is the basic starting point, right? D4x lambda over 4 factorial phi hat to the fourth plus C2 over 4 factorial phi hat to the fourth. Okay, that's the new Dyson's operator, which it's a good exercise. What I would do, I would write this down in perturbation theory. I would expand it, and I would see if I can match it up to this Lagrangian, if this count. I would check all of these things. It's one thing for me to write it on the board and say, oh yeah, this is the counter term. Just subtract it from the amplitude, see what happens. So it should just cancel all of those 3 terms. Sorry, it should just cancel the 3 ln squared in that amplitude, right? Okay, and so now the S matrix expansion includes these counter terms, and you can even draw a Feynman diagram. So a Feynman diagram to represent this, it's almost like you're correcting the vertex, all right? So we draw it like this. So this would be C2, right? And at the vertex, you would get a minus I C2, right? So the way we interpret this in field theory language is we're correcting the vertex. That's one way to look at it. And that's how you draw the Feynman diagram for this counter term. Are we good? Do you feel that this is an easier lecture than what I usually give? Or same level? Okay, good. Maybe I'll follow LB a little bit more. You should have seen my original renormalization lecture. It was bad. It was really bad. So I said, I want you guys to really understand that, because this is such a ubiquitous procedure, right? Because all theories need to be renormalized. That is so ingrained in the way we do QFT, because then how do you extract anything? We got lucky with Schwinger's calculation. That was one example of a loop level calculation that didn't diverge, just so happened, but most of them do. Okay, can I erase the board? Okay, great. Okay, excellent. So I think the best thing to do is let's just write down that amplitude. Let's write down that amplitude and then how do I even want to really write that? Okay. I'm not going to write. This is just too elementary. You write down that amplitude, the original long amplitude we wrote, right? Okay. And so now you take that amplitude, right? And you let that amplitude go to IM plus IC2. You add the counter term, which really means minus, right? Because the counter term has a minus sign. So just don't get confused with the signs. Okay, and then you find, just very simply, that your amplitude now to second order, let's say to second order, is equal to what? Minus I lambda squared plus minus I lambda plus IA lambda squared, lns minus lnt minus lnu. Right? You find that all of the capital lambda dependence is gone. Okay, that seems good. That's what we wanted. Okay, so that is the, and I'll just write this down again. What was the counter term we wrote down? Minus 6 IA lambda squared. Okay, so just work that out on your own and make sure that that makes sense to you. Okay, so let's now talk about the consequences of this, right? But this is just a simple thing. I'm not gonna go through that. Okay. Okay, so let's set aside the physical consequences for 1 minute. The first thing we need to ask ourselves, and I think I mentioned this a while ago, the intuitive student would immediately say, Kyle, fine. I get this, it's totally okay. Let's forget about all of my physical doubts. But wouldn't you get infinite counter terms? Okay, and I think I've mentioned this to you guys before, briefly, wouldn't you just, right? If you keep going in higher order in perturbation theory, let's go, I go to not just second order, not just tree level, but let's say I go to third order, fourth order, fifth order, sixth order. It seems as though your counter terms are going to just spike like crazy. I mean, and it turns out that that's not true. That certain theories, this has been rigorously proven, which even frankly, I don't understand some of those arguments. They're very, actually mathematicians prove this, not physicists, so it makes sense. Mathematicians, by the way, have been fascinated by quantum field theory. There's many mathematicians work on the, quantum field theory has no rigorous structure. It's not like general relativity where you have differential geometry. There's no rigorous structure to QFT, which makes sense because physicists invented it. But they found, and this is the miraculous thing, which I encourage you to read about, that quantum electrodynamics, all of our physical theories have a finite number of counterterms to all orders in perturbation theory. That you only need, in QED, you only need 3 counterterms to determine the whole theory. This is just incredible because it's just so happens that that's how the divergences work. And someone tell me the only theory where this doesn't happen? This should be so obvious to you now. You don't have to know why, but there's a big problem in physics with one of the forces. So what is that force?
Gravity.
Exactly. And so the main mathematical issue with gravity, now we can actually tell you the mathematical issue with gravity is it's not renormalizable. I cannot even frankly, to second order in perturbation theory, I almost need an infinite number of counterterms. It's the divergences are so complicated, and that part of that has to go with the structure of the Einstein equation, the structure of which I had mentioned to you guys last week, that it's highly nonlinear. That's part of the reason. Whereas quantum mechanics is linear, it's a linear theory, and most of the extensions of that are linear, not GR. So. Okay, so we have a finite number of counterterms, and that determines whether a theory is normalizable. Okay, so let's look at a more complicated procedure now, and then we're going to make our way to discussing the physical aspects of this. What have we actually done physically, which is a very important question to ask. So let's look at this diagram.
Wait,
Which, by
can
the
I
way,
ask?
Sorry.
For gravity, what about when you just like cut off lambda instead of trying to get rid of it?
Good. What if you cut off lambda instead of trying to get rid of it? So actually what you'll see, and this is my sleight of hand, I've said that getting rid of lambda has a physical consequence, right? So you can't simply, what we've done is we've gotten rid of lambda, but I haven't told you what happens when you get rid of lambda. Okay, so if you just get rid of lambda in the gravity theory, in the gravity case, you don't get results that make any sense. In other words, to get rid of lambda, so okay, how many counterterms did we need here to get rid of lambda? Just one, okay? You can't do that in a gravity theory. You can't add one counter. You would have to add an infinite number of counterterms. So that's the idea. You simply can't get rid of it. It's the structure of the divergences. You guys will see this, because the little project I'm going to give you is to work out why naively quantizing gravity doesn't work. That's what I want you guys to figure out. I'm going to guide you through it in a document, but that will be the project you guys will work on, and you will see, and you will yourself see that it doesn't work. So that's the idea. So you'll see, but that's a good observation. Why not just do the same thing? Right? So unfortunately, it just doesn't, it works at tree level, actually, ironically. But again, at tree level, fine, but we can't really get any, I hope you're starting to observe this. Really, the fun happens at loop level, right? Tree level is sort of like, okay, you need it, obviously, for the full story. But the real corrections, like the important corrections, don't come in until loop level, right? Vacuum polarization, all of the little things that make the theory well defined don't come in until loop level. So it's difficult to ignore that. Well, you can't ignore that. It's not you need a theory that's consistent to all orders in perturbation theory, right? Otherwise, it's very difficult. So yes, that's a good observation, but unfortunately, we tried. Okay, so let's look at this Feynman. Let's look at this Feynman diagram. And I actually never saw this kind of diagram until Lancaster. Hey, you learned something. And I've read a lot of field theory books. So it looks like this. I've never really seen this kind of thing. This momentum is P. Okay. Call this Q, call this K, call this P. Okay. So this internal line I'm calling Q, this internal outside like looping line I'm calling K, and this line I'm calling P minus K minus Q. And they call this a Saturn diagram, which is interesting. I never saw this before. I wonder where they got this from. Maybe they made it up, who knows? Okay, and so now let's run through the calculation. Let's compute an amplitude, okay? And let us renormalize it, okay? So let's just go through the whole procedure for something more complicated than the other guy. Okay, so what is the amplitude going to look like? It's going to be Im equals minus I lambda squared over 6. This is just coming from, I'm just pulling out factors. Integral from 0 to lambda d4q 2 pi to the fourth, d4k 2 pi to the fourth. Okay. I over q squared minus m squared plus I epsilon. I over k squared minus m squared plus I epsilon. You know, the best way, if you're ever confused about a Feynman amplitude, what I like to do, look at the propagators and look at the moment, what's going on with the momenta. That just tells you how everything is structured, right? That's the best way to do it. Okay. I p minus q minus k squared minus m squared plus I epsilon. I don't know why I keep writing the I epsilon. Okay, so now okay. This is a little more complicated, right? And you go, oh my gosh, how do I renormalize this? This is more challenging. This is more difficult. So now you should intuitively say, oh my God, we need some system to renormalize. We need an algorithm, right? Because, okay, in the very naive, the most basic example that you could show to a freshman in high school, right? If you just taught them about Feynman diagrams and actually, never mind, if they knew what an integral was, it's a little, I'm being a little zealous, but meaning the very basic example that I could show to someone in an hour, right? Who didn't know about quantum field theory, is easy. You just make up a term. The minute we start getting more complicated, it becomes, I mean, I don't even know right off the onset. Of course, I'm going to get, this is logarithmically divergent. It's very obvious, but I don't really know how to handle this. So there's a great trick that we can use. And that is that we can write down the integrand of any Feynman integral in a Taylor series expansion in terms of powers of p. Okay, what do I mean by this? You'll see. So let's just go slow. So I can write we'll call I the integrand as some Taylor series of alpha plus beta p squared, call this rho, not rho because that looks like p. We'll call this sigma p to the fourth plus dot dot dot. Okay, I can write out the integrand in this way. This is just a Taylor series, right? Keep adding. This would be then rho to the sixth, then rho to the eighth, blah, 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 blah. Okay, just stay with me for a few minutes. You'll see why I'm doing this. This is going to help us come up with an algorithm for writing down renormalized things. And now the key is we need to find the counterterms. Okay, so now what we can do, what happens in a Taylor series? The reason this is so helpful, because this is misleading. In a Taylor series, what are you doing? You're expanding in a power of something. Here we're doing momentum, that's where the dependencies are. Well, P, Q, K, whatever. Okay. But what are you doing? You're differentiating as you go along, right? First term is first order, second order in p squared, you've differentiated twice with respect to p, right? Then in the p to the fourth term, you differentiate twice again with respect to p. So the hope is that, does that make sense? Is that okay? That's just a Taylor series. I'm just different. So the hope is I keep differentiating this integrand as I go in the Taylor series until I get rid of the divergence. And then I know that I can go term by term and renormalize it term by term in this expansion. Is that okay? Which you should do. I mean, you can just see, because in derivatives are easy. They're just pulling some powers down, some powers up. It's very simple. It's easy. So that's what we're doing to the problem. So let's see. Let's discuss this now. I should probably have kept that up, but who cares? Okay, so again, I have some integrand. I'm going to Taylor series expand it now. And we know that Taylor series expanding something involves taking derivatives of the integrand. And the hope is that we can stop at some order in this Taylor series expansion when the integral is normalized. Is that okay? Okay. Okay, so in the I equals alpha term, in the standard alpha term, this guy's divergent because I have 8 powers. Oh, let's see, I should have kept the thing. Let me rewrite the amplitude. I want to make sure I'm D4K. I'm not gonna bother with all that stuff. D4Q, what was it? I K minus M, right? Then some I Q minus M. Of course, these are squared. Then some I Q minus M minus K minus P squared minus M. Okay, don't write the, oh shoot, squared. Okay, fine, whatever. This is the form, right? Of the amplitude. Good. So the I equals alpha term is divergent because I have 8 terms of momenta up top, D4K, D4Q, right? And I only have 6 terms of momenta in the bottom. 2, 4, 6. That's it, divergent. And the alpha term is just the first term. I haven't done anything to it in the Taylor series. Good? Okay. That's why I should have just kept, because it's good to see it in the structure of the amplitude, what's going on. The other stuff is just factors of 2 pi and all of that. Who cares? And I epsilons. Okay, if I differentiate this twice, this is still logarithmically divergent. Okay, why? The top momenta will reduce by 2, right? Because it's a power rule, the thing goes down by 2. But then I just have even powers, top and bottom, and I just get a log, and that's divergent, right? From 0 to some large number, which we saw. So now I've changed the divergence, still divergence. So to order beta squared, beta p squared, it's still divergent. Fine. Now I differentiate it twice again. So this is the 3rd term in the Taylor series. I'm obviously not doing the calculation. I'm just intuitively telling you, which makes sense. Now I lose 2 more powers again, just from the power rule. And now I'm okay, right? Because now I have what? 4 powers up top and 6 powers in the bottom. I'm fine. I don't have a divergence. So at this order in the Taylor series, I have no divergence. Are we okay with that? So in some sense, I only have to renormalize the first term and the second term. So I only need to, how many counter terms do I need? 2, exactly. That's the beauty of this process, right? And who cares about the 3rd or 4th order and 5th order terms? If you care, go knock yourself out. So differentiate these guys and just, rewrite the integrands. Good? Okay. So now we know that we need 2 counter terms. One that takes care of this. This is what we call a quadratic divergence. That's the first divergence I showed you, right? Where the power up top is larger than the power in the bottom, right? And this is called a log, well, we know this is just a log divergence. Good. So this is a very nice feature of these Feynman integrals that we can't, you can't always do that with any integral. This is just a good, actually you pretty much can. You can pretty much expand any integrand in the Taylor series, why not? You can expand anything in a Taylor series, right? So why can't you expand an integrand? Does it help to see the form as I explained that of the amplitude? Okay, very good. Okay, can I erase? So now we need to find two counterterms, one that fixes quadratic divergence in the alpha, and one that fixes the log divergence in the beta p squared term, which I really hate the way they write out this Taylor series in the book. There's better ways to do that, but whatever. I just explained what has to get across. Okay, good. Okay, so let's do that. We already kind of intuitively know what the counter term for the log should be. That's easy. But now we need to kind of discuss the second one. So let's do that. Okay. Right, so you integrate 4 times and we get a convergent integral. That's awesome. So we only need 2 counter terms. And so I can write down a new Lagrangian. We'll call it LCT for counter term. And it will be like some a over 2 d mu phi squared. Right, so a will be the first counter term plus b over 2 d mu phi squared. Right? So now I have 2. Okay, now I'm going to go to momentum space. So let's rewrite this in momentum space. So d mu 5x squared, because in momentum space, these calculations are better anyway. In momentum space, I rewrite this as phi tilde p squared phi tilde of minus p. That's just a Fourier transform. Or doesn't matter. Okay, and then therefore in momentum space, b d mu phi squared goes to p squared b, and then a just goes to a. You just get that extra factor of p squared. Okay. I'm just writing this in momentum space. Okay, and then so the let's write the renormalized Lagrangian up top. I still haven't told you what the counter terms are. So what is the renormalized Lagrangian going to look like? It's very, very simple. You just get 1/2 d mu phi squared. So basically, I just write down the normal thing, and then I just add my counter terms. Very, very simple. Minus m squared over 2 phi squared minus lambda over 4 factorial phi to the 4th plus my first guy, a over 2. So now I'm just going to add the counter terms. Minus b over 2 d mu phi squared. So I literally have just added the counter terms, right? Plus c over 4 factorial phi to the 4th. So this is just a standard counter-termed up Lagrangian. Each term gets a counter term. Each term gets a counter term. 1, 2, 3, 1, 2, 3. Good? Okay. And what do these guys differ by? All they differ by are coefficients, right? A, B, and C. I leave it as an exercise to write down the 2 counter terms for the Saturn diagram. See if you can figure them out. I have the answer. They didn't show it in the book, So see if we can figure it out. Was this okay? Okay, so now let's talk about physically, what are we even doing here? That's what we'll end on. The procedure seems simple. It is pretty simple. Not a sort of mystical thing. What is mystical is what happens physically. That's mystical. There's a very easy intuitive answer. All we're doing here is shifting parameters, right? Because we're just adding a new term, that's just shifting the parameter. And so what we do, or what we try to construct our theory, the way in which we try to construct our renormalized theories is to say that the shift in the coupling and the shift in the mass that is accrued from the counter terms gives you the physical mass and physical coupling constant, gives you those physical numbers, okay? So what I'm trying to say, this is abstract, so you should definitely look into it more. I'm going to show you a calculation, but everything we've been working with, but I think I've even mentioned this. So all the couplings, all the masses we've been working with, we refer to as bare couplings and bare masses. You can look up the term bare coupling constant if you want to read about it. They're non-physical. To make them physical, you go through this process of renormalization, and adding the counter terms shifts the parameters such that you get the physical quantities. That seems like, well, all you've done is a sleight of hand, but it's true. That's what we're doing in effect. So a renormalized theory gives you physical quantities, and I would look into that more to get more details. Okay, so let's see how that works briefly. So let's go back to our Lagrangian. Okay, so let's just start here. Now let's write down a renormalized Lagrangian. We'll call it L prime. And what I'm going to do is I'm going to label these guys a bit more explicitly. So we'll say that phi sub little r is the renormalized field. And now instead of M, we'll call this MP for the physical mass. And we'll call this lambda P for the physical coupling. Okay, and of course, we need to add our, oh shoot, why do I always mix up these signs? Sorry. These should be minuses. Okay, and let's just add our counter terms. For consistency, let's call these all little r. Okay, so this would be the standard form of a renormalized Lagrangian, right? Just the general form. Okay, where phi sub r are the renormalized fields. Okay, and basically, it's a very good exercise to do this. I'm just going to show you the final result, but you should follow this computation that gets you from the unnormalized fields to the renormalized fields. It's not an easy exercise. You can find it online, but there should be some procedure, right? You should intuit it. You should say to yourself, okay, there should be some procedure that takes me from normalized fields to renormalized fields and backwards, right? You should be able to do that. And you find that basically all you need to do is shift the parameters. Okay, so you find that m squared, so I'm just going to write down the final shifts in the mass and the coupling. So m squared equals some delta m. Okay, that's just some shift in the original parameter plus the physical mass over 2. You can look this up and compute it. Wait, over 2 or? You see, I mixed up my 2's and z's. This should be a z, where z is just, I'll tell you, where z is defined as one plus delta z, and then z is just some, how do I say this without math? Z is some auxiliary parameter. It's just some random constant that we can multiply by, right? And where phi is now defined as square root of z phi r. Okay, so you go through this calculation, just plug in and work it out, and this is what you'll find. And you should go into the book and read this, but I'll tell you the physical meaning. You'll find that m shifts in this way, and then lambda shifts in a very similar way. Okay. So the coupling shifts in a very similar way, where you get lambda p plus delta lambda over z. Okay, where z is that same. Wait a second, that should be squared. Okay. Okay, so sparing the details, what happened? My original coupling gets shifted, right, by some arbitrary parameter with the physical coupling and physical masses incorporated. That's it. Now you're saying you're probably going, and you're rightfully so, well, how do you get what is Hi, can you guys hear me now?
Yeah.
Okay, good. Sorry, my internet went off for some reason. Okay, where did I cut off? Where did I cut off? Am I good? Can you guys hear me? I can't.
Yeah.
See, I can't see.
Trying to
you.
remember.
Oh, okay, because I can't see you guys because my computer the internet went off. I'm on my phone now. Okay, whatever. I'll just explain this. So, yeah. So you have the original mass and coupling. This is what you calculated. Sorry, not what you calculated. What you start with, and in order to get the physical parameters, you have to shift. You have to shift the original parameters accordingly. And that is determined by the counter terms you add to the Lagrangian. Okay, that's the basic principle. Okay, so that's the basic idea behind renormalization. It's a very, it's mysterious. You need to read about it more. I think you guys should see some more examples, which you'll see today in Johnson's session. Okay, good. My computer is back up. So let me join back that way because it's oh, now it's not connected again. Oh, I don't, maybe someone's messing with it. I don't know. But it's good practice to see some example. Okay, it's back up. Sorry. This never really happens, but when it happens for real. Because it's very hard for me to just look at the phone because I can't see you guys. There we go. Yes, I know. Okay, it's good now. Ah, the pitfalls of Zoom. Crazy. Okay, good. Yeah, so this, as I was saying, this is the basic principle behind renormalization. But I think it's very important you see some examples. So do go into the book and look into that. But all it corresponds to is just finding the right counterterms. Okay, it's a very simple procedure. It really, it's actually miraculous that it's this simple. It should have been harder, but whatever. Okay, anyone have any questions? Okay, good. Okay, so next week we're going to do symmetry breaking. Okay. Then we'll do the renormalization group and the path integral. Actually, we'll do the renormalization group, but in order to do that, you should know about the path integral. Okay, so please read about it. Then we'll do the weak interaction, so electroweak unification, which is the unification between the electromagnetic and weak force, which was done by Glashow, Weinberg, and Salam. That's one of my favorite topics because we get to talk about crazy things like hypercharge, isospin, things that mean nothing to the experimenter. It's funny because if you ask an experimenter, have you ever detected isospin? They're going to say you're crazy, but we use it as theorists. Then QCD, Yang-Mills theory. And then I want to do some special topics to conclude. So the two special topics I want to do are topological field theory, which we can do because we know some GR, and magnetic monopoles. That's a fun one. So yeah, that's it. So I think we'll be done in a month, which I think the last class on the syllabus was when? September, May 2nd, right?